Okay, so welcome to Chem 120. This is Chemistry and Society, and this will be our first lecture on Unit 1. The first part of Unit 1 talks about the scientific method. And whenever I would take a science class, I would go through the scientific method and the hypotheses and the theories and laws and models and all that stuff. And I was always so excited for these classes that I just wanted to get through this. But it is really important to take a little time and examine the scientific method, because without it, we wouldn't have all the understanding of science that we do now. So it's very important to understand. So science is an accumulation of knowledge about our world, and chemistry is the study of matter and its changes. For example, why does iron change into rust? Why does sugar dissolve in water, but oil does not mix with water? So hypotheses would be more than one hypothesis. Hypothesis is just one. So a hypothesis is a guess or explanation of data and observations. So when you develop a hypothesis, you need to test it. So let's say you have developed an arthritis drug, and you're pretty sure that it's going to be effective in treating arthritis. So when you're designing a test for this hypothesis, you need to build in a control. And so what does that mean? Well, that means that if you're going to test this drug on different patients who have arthritis, you need to have a set of patients who are taking the drugs and who aren't taking the drugs. So for those who aren't taking the drugs, they would be given what's called a placebo or a pretend drug, so like a fake pill. It might be, instead of containing the drug that you've made to treat the arthritis, it might be just sugar. So you would carry out the test for a number of weeks, however much you set out to in your design, and then you would consult the patients. How's your arthritis? How would you rate it? Is there any improvement? And if your patients who took the drug showed an improvement in their arthritis versus the patients who didn't take the drug, they took the control, then you could say, okay, it's likely that this drug is effective at treating arthritis. So I'll just give this example for our definition of a control test. So example, arthritis drug tested on two groups. One is a test group, takes actual drug. Two is the control group, takes placebo. Now, one thing that you would need to be sure of is that these patients are of similar age, weight, health, diet, and exercise. Age, weight, overall health. You wouldn't want to have patients that have a variety of health issues. That would make it hard to determine what's going on. So health, diet, and exercise. And when I say diet, I don't mean the latest diet craze, no, I just mean what they consume is pretty similar. So a control test is something that's possible in the fields of pharmacy and science and drug design. The control test is not as applicable to fields such as politics or economics, because these fields have variables which cannot be controlled. So it can lead to difficulties interpreting the results or forming hypotheses. So another thing when you're designing your experimental design, you need to make sure that your experiments are reproducible. So reproducibility is that the experiment is carried out over and over with the same results. So experiment can be carried out over and over with the same results. Okay, so scientific theories are a general explanation of phenomena. So generalized explanation of phenomena. Okay, so for example, the atomic theory states that in chemical reactions, matter cannot be created or destroyed. This is based on many experiments where materials were carefully weighed out before a chemical reaction, allowed to react, and then carefully weighed out after the reaction was over. As long as the measurements were careful enough, it was always found that this weight did not change from before the reaction to after the reaction. Nothing was lost or gained. So a theory is tentative. An experiment may be done tomorrow which disproves this theory, or requires that the theory be adjusted to some extent. So scientific theories grow and change as we learn more about nature, and we are able to do better experiments using new technologies. So tentative, what I mean is that it can grow and change with knowledge gained. That would be the theory. And a law is a mathematical statement of a theory. I'll talk a little bit more about that in just a second. Okay, one more thing about tentative, and then I'll talk about the law. Okay, so we're talking about the theory of gravity again. So that explains why things fall when you drop them. And by the way, if you're concerned that you need to know these stories, we will eventually get to these, but I'm just using these as examples to explain the scientific method. So the theory of gravity explained why things fall when you drop them and why the moon orbits the Earth. As we built better instruments to measure the speed of light and examine objects moving very fast, the theory of gravity needed to be modified. A more general version, the theory of relativity, was developed by Einstein to explain how gravity is modified at very high speeds. So that kind of explains how it's tentative. It's not that the theory was rebuked or found to be false. It just was that, oh, it turns out at high speeds something else is going on versus at low speeds. Okay, so in science, a theory is based on many observations that is tested by many experiments, and its common usage outside of science. The word theory is often used in a more relaxed way. Someone may say, I have a theory why my friend didn't call me last night. In science, you would actually say, I have an idea of why my friend did not call me last night. A theory has the support of many experiments, which is able to explain rather than being an idea a person just comes up with. Theories do not grow up to become facts. Gravitation is still referred to as a theory, although everyone believes in it and most people would treat it as a fact. A law is a mathematical statement of a theory. It is possible to calculate the force of gravity, the weight of an object, how fast something will fall when you drop it using the law of gravity. Again, outside of science, in common usage, law refers to a different concept, especially when you're talking about attorneys and tort law and all that. Okay, so scientific theories, since they are based on experiments, deal with things that can be observed and measured in an objective way. Things that cannot be measured, emotions, spiritual concepts, cannot be treated by science. My husband loves science for that reason. He is very objective, control experiments. So it always makes me laugh when I talk about this. Okay, so a scientific law, I'm just going to restate this, is a mathematical statement which summarizes large amounts of data. Mathematical statement which summarizes large amounts of data. For example, the law of gravity states that the force of gravity is equal to a constant times the two masses of the two objects divided by the distance between them squared. So it's F equals G times M1, M2 over R squared. This is a mathematical relationship based on many measurements and experiments. So this is the formula. I do not expect you to memorize this. But so that's a scientific law. All right, a scientific model is a picture or model helped to visualize a process. So an example of this, we often picture planets as round balls circling the sun. In reality, the planets are not perfectly round balls and have more complicated motions rather than circular, but the picture helps us visualize a process that we cannot easily see directly. Okay, so that is the scientific method. So moving on, we'll talk about risk-benefit analysis. Now, risk-benefit analysis is a way of determining whether or not the benefits of a technological or scientific advance outweigh the risks. So, this is a way of determining whether or not the benefits of a technological or scientific advance outweigh the risk. And we are really making huge advances and strides with technology nowadays. So this is an important process. And there's several science fiction novels written on this. I always think of Jurassic Park. You know, they didn't think about whether or not they could keep these dinosaurs in captivity. So the way this risk-benefit analysis works is you look at the desirability quotient. So if you have a large benefit and a low risk, then it's said to have a high desirability quotient. If you have a small benefit and a high risk, that is said to have a low DQ. If you have a small benefit, small risk, that's an uncertain DQ. If you have a large benefit and a large risk, that is also an uncertain DQ, or uncertain desirability quotient. So let's go through a few examples. So a drug is developed that can suppress appetite and help people lose weight. It is later discovered that it also weakens the heart muscle, in some cases causing fatal heart attacks. So, benefits. People can lose weight, which may improve their health. So, lose weight may improve health. Then let me write out this example. Drug can suppress appetite. Weight loss. Weakens heart muscle, leading to heart attack. Okay, sorry. Benefits: you lose weight, may improve health. Risks: heart muscle weakening, heart problems. So I would say if a person needs to lose weight, there are other options besides this one medication. It would be more desirable to explore other medications, exercise, or diet before trying a new medication, which could permanently damage the heart or cause death. So this has a small benefit, large risk. So this is low TQ. So a low desirability quotient would be you don't do it. Okay, so here's another example. A drug is developed that can reduce the risks of some forms of cancer. So drug reduces risk of certain cancers. However, can also increase the risk of forming a blood clot, which can be fatal. It can also increase risk of fatal blood clots. Okay, so benefits. Risk of cancer is reduced. Risks. Blood clots increase. So if you think about this, it depends on the patient. It depends on whether there's a family history of certain cancers. Would somebody who never had cancer in their family want to take this? And then they die of a blood clot. So this one is not as cut and dry as the first example here. So this would have an uncertain DQ. Some patients may have a history of certain cancers and need to be treated with this medications, but some patients may have other options for treating cancer. Some patients may have other risk factors where the formation of the blood clot is more dangerous. There are potentially large benefits, but also potentially large risks associated with it. So you have large benefits, large risks, uncertain DQ. Okay. So this risk-benefit analysis is helpful. It can kind of make you more objective about things. So, if you ever find yourself in an everyday situation and you're trying to think, well, I want to go out tonight, but I don't want to drive, you could apply it to a lot of different situations that you find yourselves in. So that's risk-benefit analysis. Now we're going to go on to the process of science. Science is the accumulation of knowledge about our world. Science is testable. So experiments can be carried out to see if an idea is correct or not. Okay. Science is reproducible. So we talked about this on the first page. The same experiment should always give the same results. It's explanatory. So simply listing facts is not science. Science tries to find the reason behind the facts. These reasons are called hypotheses or theories. That's predictive. Science is predictive. So based on past experiments, science tries to predict the results of new experiments. It's tentative. New experiments can cause science to change. Okay. Then this does not necessarily mean that the old theories are wrong. Newton's law of gravity works very well for objects of common size and moving at normal speeds. For very small objects, like atomic size, the theory had to be changed to the quantum theory. For very fast-moving objects near the speed of light, the theory had to be changed, the theory of relativity. Newton's law is not wrong. Okay, let's consider this exercise. The scientist considers a group of people and finds that those on a diet with low carbohydrates and high fat and protein lose weight quickly. So, Atkins diet. So, high fat, protein, low carb, lose weight quickly. He hypothesizes that a diet rich in fat causes your body chemistry to switch to burning fat instead of sugar for energy. Your body begins to use up stored fat, thus causing your weight loss. Is this testable? Could you think of an experiment to test this hypothesis? So, let's see, is it testable? For example, you might set up two groups of people, one on the Atkins diet, one not. See if they lose weight. You might also test the percent body fat and see if they are losing stored fat due to a diet. So, two groups, one on Atkins, one not. You could also test body fat. Okay, is it reproducible? So could you carry out the same experiment again, or could other scientists try the same experiment? It is certainly possible to set up many groups of people and see if the diet helps lose weight and body fat. So yes, explanatory. Is it explanatory? Does it give some sort of connection between the idea and the result? In this case, the hypothesis says the diet causes a change in the body chemistry, which causes the weight loss. There is an explanation of the result. So, yes. So, let me add up here. lose weight quickly due to change in body metabolism. So you use fat stores for energy. Okay? Is it predictive? Can it predict the results of other experiments? In this case, somewhat. You might predict that a diet high in carbohydrates and low in fat would cause body chemistry to switch to storing fat and would cause weight gain. So, somewhat. Okay. Tentative. Is this tentative? Yes, someone could discover tomorrow that there was a different explanation. Maybe those people on the Atkins diet also exercised, or the explanation is incomplete. Diet causes the body chemistry to change, but the change is due to increased burning of carbohydrates, not increased burning of stored fat. So, there's an example where using the process of science, you can learn more about what is going on. Okay, so let's go through another example. And I'll do this on the back of this page. Okay. A scientist says that crop circles and cornfields are made by aliens who land spacecrafts in the middle of the night. Crop circles caused by aliens in spacecrafts. Okay, so is it testable? Not really. How can you set up a controlled experiments and have aliens land in one field but not another? So, not really. Maybe you're laughing at this. I think this one is a funny example. Reproducible. Is it reproducible? Not really. Although there is more than one crop circle, you cannot create more as needed or compare different aliens. Not really. Is it explanatory? Somewhat. Says that aliens created the circles, but does not explain why an alien would want to do that or what the purpose of the circles is or whether or not aliens actually exist. So, somewhat. Okay, is it predictive? Not really. We cannot predict whether or not more circles will be created, where they will be created, or what will happen after the circle is created. Is it tentative? Yes, there could be a different explanation, like someone playing a joke, or more evidence could be found. Someone actually sees and videotapes the aliens creating the circles, or the aliens contact us and explain the circles. Okay, so you get an idea of where this scientific method and the process of science can be utilized. Okay, so let's move on to critical thinking. So this is to test claims. This is used to testing of claims. So, falsifiability. Is it possible to prove a claim false? Can you come up with an experiment which can test this claim? So this is not the same as saying the claim is false. Falsifiability asks whether the claim can be tested or not. So, testable or not. So example, a man claims that he can predict the price of a stock on the stock market 1 week in advance. So this can be tested by writing down his prediction, waiting 1 week, and then checking to see if his prediction was matched to the actual stock market price. So a man claims he can predict stock prices. So yes, can be tested. Okay, another one. A man claims that painting the walls of a bedroom blue removes bad energy from that room. Okay, this is not really possible to test for bad energy or how colors affect it. So, another example, man claims painting room blue removes bad energy. No. Okay. Logic. Does the conclusion follow from the supposition in a reasonable manner? Is there a connection between the premise and conclusion? So, connection between premise and conclusion. Okay, so an example. If I buy anything on the internet, my credit card number will be stolen and I will be charged for objects I did not buy. So this is the explanation. Buying on the internet means giving out a credit card number, and it may be possible for someone to acquire the number and use it. There is a logical connection. Purchasing item on internet means credit card number will be stolen. Yes. Logical connection. Here's another example. It only rains on Monday because I don't like rain. I don't like Mondays. And let's see. Is there a connection between the premise and conclusion? It is extremely unlikely that feelings can change the weather patterns. Also, it rains on days other than Monday. Rains on Monday because I don't like Mondays. No logical connection. Okay. All right. Replicability. Can the experiment or evidence for the claim be repeated, or is it a one-time coincidence? Can it be repeated? Okay. Example. 1 ml of pure water has a mass of 1 gram. This is a straightforward to check using a balance or scale, and has been done many times. So 1 gram of water, 1 ml of water equals 1 gram. Yes, it can be repeated. Okay. A pair of scientists claimed they could use nuclear fusion to occur at room temperature and produce vast amounts of cheap energy. Nuclear fusion at room temp? No, not possible to repeat. Okay, another example. A person claims to have been abducted by aliens last month, and this cannot be reproduced. Alien abduction not possible. Okay. And then sufficiency. Is the evidence adequate to the claim? Is there objective evidence rather than hearsay or opinion? Evidence adequate to the claim. Okay, example. A man says there will be a meteor shower during the last week of August. So it is possible to check previous years and determine when meteor showers occurred, and telescopes can be used to check for the source of a meteor shower. So this is sufficient. All right, a man says you should not drink pasteurized milk because he read on the internet that pasteurization destroys the calcium in milk. Okay, so milk, pasteurized milk. Sorry, this is so messy. Pasteurized milk does not have calcium in it based on internet. It is not sufficient. There have to be more evidence. Okay, another example. A person says that driving electric cars will remove all air pollution from the planet. So electric cars will remove pollution. Sufficient? What do you guys think? Well, there are other causes of air pollution. Changing cars is not sufficient to completely solve the problem. So it's not sufficient. So if a claim passes all 4 tests, it might be true. So if you can go through and say falsifiability, logic, replicability, I have such a hard time saying that, sufficiency. So if you can go through all of those, then the claim might be true. So you can use the acronym FLAIRS, falsifiability, logic, just a little a, replicability, and then sufficiency. So these will help you remember. If it can pass all of these, then the claim is likely to be true. Okay, so this concludes our first lecture on the scientific method, the process of science, risk-benefit analysis, and critical thinking. I recommend that you do your homework problems and come back here for the next lecture.